Hello everyone, welcome back to another video related to electronics. In this time we are going to deal with one of the most revolutionary devices invented in the last century. This is the transistor. I'm going to focus on the first transistor, which was invented in 1947. This is the bipolar junction transistor, also known as BJT. As usual in my videos, you can navigate through them. In this occasion, you are going to find three parts. In the first one, I'm going to deal with all the content that you need to know in order to understand circuits where the bipolar junction transistor is present. In the second part, I'm going to focus on a numerical example that is going to help me explain what are the different regions in which this device can work. Finally, I'm going to take all the components that are included in this numerical example, and I'm going to mount it in a breadboard. So let's go started. What is a transistor and what is the purpose of this device? Well, as a first approach, we can say that a transistor is a switch electrically controlled. As a rule of thumb, for all kinds, a transistor is a device with at least three terminals, where the large current between two of them is controlled by a third terminal. This control can be done by current, by voltage, or both of them, and that is going to lead to all the families of transistors that you have on the market. But even if the graphene transistor will appear tomorrow, the principle of working will remain untouched. That is, this device will be a device with at least three terminals, where the large current between two of them is controlled by a third one. So, without further ado, let's go to focus now on the bipolar transistor. Here we have the schematic of a bipolar junction transistor. More exactly, this is a NPN type. So we are going to play with the two kinds of bipolar junction transistor, this one and the complementary PNP. In this video, I'm going to focus on that. So three terminal, the one in the middle is the base, the one on top is the collector, and remember, the one that goes with the arrow, okay, that is the emitter. So in a bipolar transistor, the big current, large current is going to flow from the collector into the emitter. And that large current is going to be controlled by the third terminal, that is the base. So as long as you are able to provide current through the base, so voila, you are going to have current between collector and emitter. So it is very important to understand what we have under the hood between the terminals of base and emitter. And the thing that we have is a diode. A diode is probably the simplest electronic component that you are going to find. So this element has two terminals. The one that is here, that is the anode, and the other one that is the cathode. So in our circuit, in our transistor, the anode is going to be played, the role of the anode is going to be played by the base. And the role of the cathode is going to be played by the emitter. Every time that I have to explain the working principle of the diode, I usually use an analogy. That analogy involves a highway and also a toll. So imagine that our electrons which flow through the cable are going to find the diode, as a car in a highway is going to face a toll. So the only way that the car can go is from the anode to the cathode. Because in the other way around, to pass through the toll, it's impossible. So this way that to go from anode to cathode means that the anode should be more positive than the cathode. And that way of biasing this device is called forward. The other way around means that you have the most positive one at the cathode and the most negative one at the anode. So that means that the thing that we are going to work is reverse. But as you can imagine, the only way that you can have current is in a forward mode. Okay? In reverse mode, we are not going to have current. So what is the diode? It's an element which is going to block the current from cathode to anode, but is going to permit, is going to allow current from anode to cathode. Something that is important, that if you pass through, of course, you have to pay a toll, and that toll is 0.7 volt. So if at the anode you have 0.7 volt or more, okay, so the electrons are going to go through the cathode. How is that going to be, okay, translated into our bipolar transistor? So the emitter should be the most negative one, and then the base should have at least 0.7 volt. So that is going to be positive. In that way, we are going to bias this union base and emitter in forward, and we are going to have current, and we are going to activate, okay, the device. Of course, the collector should be also positive in order to ensure the current to the collector to the emitter. Now that we know the basics about this device, is the moment to dig, okay, deeply into the different regions of this component, but using a numerical example. The BJT can work in 3 different regions, that is cutoff, active, and saturation. In this video, I'm going to focus on cutoff and active. I will devote a full video for saturation. The cutoff is the simplest of the regions that we are going to work, and in this case, the union between base and emitter is not going to be polarized in the forward, so it's going to be in cutoff. So that could be that one example could be the voltage here is going to be negative, or here negative. When I say negative, I mean, for example, 0 volt. 0 volt, okay, in both cases, you don't have enough, okay, to pass the toll. And the transistor is not going to be activated. So in that configuration, we are going to find here, in terms of voltage, negative, negative, and probably here, positive in the collector. So in this case, the thing that we have is that we don't have this current through the base, so that current is 0, okay, and that it's consequently you are going to have the current through the collector equal to the current through the emitter, and also equal to 0. All right, so let's go to see example of this case with this circuit that we have here. So as you can see, you have here a switch, you have a connection between ground, this is 0 volt, okay, to the base, and the emitter also is 0 volt. So impossible for the electrons, okay, to go through and activate the device. Even considering that the voltage at the collector, okay, you have here a voltage supply and you have 12 volt, but because it's not activated, so you don't have, okay, any kind of current through the collector. So the current through the collector is going to be 0. If you are wondering what is the voltages across all the terminals, so voltage at the base, voltage at the emitter, voltage at the collector, the easiest way to analyze this circuit is considering that you can erase this device. So if you erase that device, okay, I'm going to do it here. Okay, so I'm going to take that and I'm going to erase, okay. So now the thing that we are going to have is that the voltage that you have, for example, in collector is going to be 12 volt. Okay, but because you don't have current through, the voltage at the base is going to be set by 0 volt, so the ground, and of course the voltage at the emitter, okay, remember emitter, base, collector, is going to be also 0 volt. So that is a sample, okay, that I wanted to see with the case of cutoff. Let's go now to move into a more interesting configuration, which is active. In this configuration, the thing that we are going to have is that the union between base and emitter is going to be biased in forward. So in a configuration, if we think about voltages, that one is going to be the lowest. Then the base is going to be higher than the emitter, at least 0.7, and the most positive one is going to be the collector. Remember that this one is collector. Okay. So because the union between base and emitter is polarized in forward, okay, so you have current through the base. So the current through the base is no longer zero, so you are going to have current between collector and emitter. What kind of equation we can apply in this mode? So first of all, we know that the base emitter is going to be around 0.7 volt. Okay, another important equation is that the collector is going to be beta times the current through the base. And beta is a parameter that depends on the technology, depends on the transistor, the BJT that we are using. That is a dimensionless parameter that is going to give us a correspondence or a concordance between the current that goes through the base and the current that goes through the collector. It's a factor that is a gain, a current gain between these two terminals. Okay, so finally, another important equation is the current through the emitter is going to be the current through the base plus the current through the collector. Remember again this image about the toll, okay, and you have to consider, okay, this junction here, and I'm going to make another analogy that here you are going to have the base, here is going to be the collector, and here you have the emitter. So as long as the electrons are able to pay the toll and pass through and create this current through the base, okay, suddenly the current through the collector is going to be also created, and both of them are going to be joined, okay, at the emitter. So the current at the emitter is going to be the sum of the current through the base plus the current through the collector. Then another important thing to understand that configuration is that you have to ensure that the voltage between collector and base should be more than 0 volt. Okay, so let's go to say 0 volt. In reality, it's minus 0.2 you are going to find in the literature, but I think that is easier to remember that should be more than 0. Okay, so with this equation, we can move now into a numerical example. Right, here we have a sample, okay? So it's basically the same as we had before, but now the switch is connected to a voltage supply of 5 volts. So in this configuration, clearly we can identify that the emitter is the most negative one, in this case is 0, so the lowest one. Then you have the base, probably positive, and here you have the collector, positive. Okay, important things also here is data. What is the data that you are going to have? Beta, which is going to be given, beta is 190 here, voltage-based emitter 0.66. So in these cases where it's high likely that you're working active, the first thing that we are going to do is to suppose that. So we are going to suppose active mode. So once we suppose active mode, okay, so we are going to know, okay, we know that the voltage between base and emitter is going to be no 0.7. In this case, they told us that it's going to be 0.66 volt. And also another important thing is the current base, okay, sorry, the current through the collector is going to be beta time current through the base, okay. So the way to face these exercises is suppose active, use this, find all the voltages, all the currents, and at the end verify that the voltage between collector and base is higher than 0 volt. If it is like that, so your supposition, initial supposition about the mode in which the bipolar transistor is working is okay. Otherwise, means that it's not working in active. If I consider all my experience solving problems related to bipolar transistor, and once you are in active and you have done all the supposition that I mentioned before, the key point in order to solve all the and find all the values and voltages and the current, the key is to find the voltage at the base. So if you are able to find the voltage here, voltage up the base, okay, suddenly everything is going to be easier, okay? So let's go to focus on that. In this case, it's very easy because in all the problems where the emitter is directly connected to the to ground, okay, it's going to be very easy. Look, so from the first equation, I'm going to say that the voltage base emitter, I can split that, and this is voltage base less voltage emitter. And all of that we know that is 0.66, but the voltage at the emitter is 0 because it's connected to ground, so that is going to be cancelled. So suddenly we are going to get, okay, the cornerstone in order to solve this, okay, this problem. So now we know that the voltage is 0.66 volt. At the point that we know what is the voltage at the base, suddenly the current through the base can be found, because the current through the base is going to be, if you look at this resistor, this is the current that goes through there. So it's going to be the origin, what is VB, okay, less the voltage at the base, divided into the resistance, okay, R1. So that means that this is 5 volt less 0.66 divided 100 kilo ohms. Watch out with the power, okay, power 10. And now if you do that, okay, the result is going to be more or less 43 microamps, which is something the value, typical value for current through the base. So current through the base when you are inactive should be in the range of microamps. In the same way, the current through the collector as well as the current through the meter is going to be in the range, okay, of milliamps. This is the normal range of this mode. Okay guys, so what is next after finding the current through the base? So now the idea is to use this equation that you have here, the second one. So the current through the collector is going to be beta times the current through the base. So this is, that is 190, that is given, multiplied by 43, so 4.3, sorry, micrograms. If you do so, that is more or less 8.2 milliamps. So milliamps, micrograms, everything works. If you combine this equation with the one that is that one, okay, the sum of all the currents, you are going to find that the current through the meter is beta plus 1 divided beta current through the collector. If you realize this ratio that you have here is going to be more or less, that is going to be more or less 1, okay, as long as beta is high enough. What is high enough? To me, beta higher than 50, okay, is going to be big enough. Big enough to say that current through the meter is going to be more or less current through the collector, because in our case it's almost 200, okay, so that means this is more or less also current through the meter. So now we know all the currents, current to the base, current to the collector, emitter, and the only thing that left is the voltage here, the collector. But the voltage to the collector in this case is very easy because you have a direct connection to the VCC. So 12 volt, right. At this point that we have everything is the moment to say, all right, are we really working in the active? So to do so, you have voltage to the collector base. That is the thing that you have to check. So this is voltage to the collector less voltage through the base, and this is 12 less 0.66. Remember that this is the voltage to the base, and it is more or less 11.3 volt. So yes, we do work in the active mode. So everything right, everything okay. Next step is to take all this design that we have here, both of them, okay, because it's very easy, it's the same. Just to, to switch here to one position to another, and check that everything is going to match. So the result here that we have done are going to match. I invite you, okay, to do the simulations with whatever software, and in this case I use Multisim by National Instrument, and check that the simulation are going also to result from the simulation are going to match, okay, with the one that we have done here. So if you look here, all right, so you have values which are very similar to the one that we have found. Let's go to see if with the breadboard and everything that surrounds its circuit, everything is going to work fine too. Let's go. Here we have our experimental setup. As a transistor, I'm using the very well-known 2N2222 with a package that is a metallic one. By the way, I love this package because you have an extra piece of metal in this corner, which is going to indicate the emitter. In the middle, you have the base and then the collector. With this extra piece of metal, it's impossible to switch collector by emitter. That is the typical mistake that many beginners make in the laboratory. Then I have here a resistor and then my power supply with two voltage sources, one that is set at 5 volt, the other one at 12 volt. Then I have a voltmeter and then an ammeter. The voltmeter is measuring the voltage at the base, and the ammeter is measuring the current through the collector. If we check the schematic, we are going to realize that we have right now a connection between this point, okay, and this other. So 0 volt here, consequently 0 volt here, 0 volt also, so no current through the base. So it is in cut-off, and the only point is to verify that at the collector you have 12 volt. Let's go to measure that. So I have here a cable to do this thing fast. Here you have, so 12 volt at the collector. So everything as we expect. Not rocket science. So let's go now to move into active. So to trigger active mode, the thing that I'm going to do is to connect this terminal of the resistor, okay, to 5 volt. So in our circuit, the connection that we are doing right now is that one, from here also to here, as it's represented in this unit. Okay, so before keep on going, let me remind you the values that we compute, okay, which are there. Let's go to check what values we are going to get. So voltage at the base, right now it's 0.6, more or less, okay? It's moving a little bit, 0.6 volt. We got 0.66, but this is a voltage given by the manufacturer, okay? So that depends on the current that goes through the base. The collector, let's go to move that into collector. That is not going to be different from 12, so 12 volts, no problem. Also the meter is not going to be different from 0 volt because it's connected directly, okay, to ground. A little, okay, chain is going to happen. So also 0 volt, that is everything correct. Let's go now to move into the collector. So this is the current, it's connected there to the collector, and we have 9.7 milliamps, which is the typical thing. To the meter, we are going to get more or less saying a little bit more. Okay, I'm not going to do it because the important one here, and probably the most difficult one to measure when you have to do some kind of measurement with a bipolar transistor, is to measure the current through the base. So remember, to measure whatever current, first thing that you have to do is to break the circuit. So I'm going to break the circuit here. I have to disconnect my ammeter where it was, from here the negative, here the positive. That I'm going to return to the place. So this is VCC. And now the idea is the electron should pass through this ammeter, so positive here and negative in the place where that one was, was with the resistor. All right, so no measure through, but the point is now the current has dropped a lot. So it's 20, it's beta time less. So that is 200 times less. So we have to move the scale. But when you move the scale, voila, everything works fine. And the current that we got, it's 45 microamps, which is very, very close to the one that we got. That is 43 microamps. So everything works as it was expected, and I hope you enjoyed this video related to bipolar transistor. Remember that I'm preparing you are going to find a second part, okay, just dealing with saturation. Thank you a lot for watching this video.